Okay. So we are going to start with what we call as transportation problems. Okay. Now, basically, as the name says, uh, this is, in fact, these kind of problems are basically an application of linear programming problems, which are used when we are transporting goods or material or anything from one set of sources to one set of destinations. Okay. So as I said, most of the applied maths, that includes statistics also, this saw its applications and development mainly when in the time of Second World War, because prior to that, what was happening was theoretical development of mathematical models, and in the field of pure maths, a lot of research was being done. But unfortunately or fortunately, because the need was not there, so the applications could not be seen where these models can be applied. But at the time of Second World War, the need was felt to apply those models and proceed systematically and scientifically. So because of that, the growth of applied maths, it started from there. And after that, once the things were applied in one particular field, then gradually the industries, and because after the Second World War, we had to talk of industrial revolution also throughout the Europe and all. So the researchers, they felt the need to apply it in the production sectors as well. So that is how the subject has developed, and it has grown over a period of time. So like the need was felt because like the arms and ammunitions and everything, even the man force was to be transported. So we had different sources where the things were located, and we had various destinations where the things were to be transported. So even the food material, the medicines and everything, like at the war front, it had to be supplied. So what we do normally in case, or what is done in the case of transportation problems, is that we have fixed number of sources. That means where the things are kept. It could be the warehouses also. Like this is what Amazon is doing now. So we have warehouses where the products are kept, and we have destinations where they have to be supplied. Okay, so say supposing we have m number of sources and say n number of destinations where the things have to be supplied. Now, when you are supplying from, say, if I have m number of sources, that means I'm talking of sources like, say, S1, S2, Sn. I have m sources, and I have n destinations where I need to supply the things. Let's name them as D1, D2, Dn. Okay. Now, that means like let's use the suffix I for the sources, and let's use the suffix J for the destinations. Okay. Now, what happens is that if I am, transporting something from, say, ith destination, ith source to the jth destination, obviously there is a cost of transportation involved. Okay, so this cost could be, I mean, it could be total inclusive cost of everything that needs to be transported. So supposing per unit cost of transportation is say AIJ. Okay, that means AIJ becomes your cost of transporting 1 unit of your good from the ith source to the jth destination. Okay, so that means we are aware of the cost that would be involved in transporting those goods, number one. Secondly, what happens is that the sources here have what we call as the availabilities, because things are available with the sources. Okay, so we have fixed number of availability, that is available with the sources, and we have fixed number of demands that these destinations have. Maybe the destination D1 needs some fixed amount of demand. Say, let the total demands be small d's, okay, and let the total availabilities be small a's. Okay, so that means source S1 cannot supply more than A1 units. Source S2 cannot supply more than A2 units, and so on and so forth. Similarly, the destination D1 needs only small D1 units. It does not need more than D1. Okay. Similarly, the destination D2 needs only small D2 number of units, and so on and so forth. So they are their demands, and this is the availability with the sources. So they are going to define the limitations. Okay. Say it could be like, I don't know which source should supply to which destination, so that the demands are also met with and the availability is also exhausted. Okay. And of course, the cost of that transportation turns out to be the minimum. Okay. So AIJ becomes the cost here. So one thing is very clear, that in these kind of problems, we have to talk of minimization problems, because every time we would be minimizing the cost of transportations. Okay. So basically, the objective here, or the decision variables here. So like it will be converted into a linear programming problem only, but then we have to, as I said, we have to talk of the decision variables. So what we define here is, obviously decision variables will not be 1, 2, and x1, x2, xn in this case, because we have two sets of, we have two basic sets, from and to. Okay. So definitely my decision variables will also be defined like this. Okay. So the variables that we define here would be like something like, we'll say let xij be the number of units, to be transported from the ith source to the jth destination. Okay. Now, if xij is the amount to be, the number of units to be transported, and aij is the per unit cost involved, so that means the total cost involved is going to be aij xij. Okay. So that means aij is known to us. They become the coefficients. Xij's are the variables, because this is what we have to find. Okay. And we have to minimize terms like this. Okay. But how many such terms? I varies from 1 to m and j varies from 1 to n. Okay. So it's like we have the problem is going to, typically the problem is going to look like something like this, because we are going to have a transportation table, something like this, where these will be my sources, S1, S2, Sm, and here I'll have my destinations, D1, D2, Dm. Okay. So this is how a typical transportation problem is going to look like. I'm sorry, because of my pain, I'm not able to write properly. Okay. So what we do here is, I mean, you can call A11 or C11. The choice is absolutely entirely yours. So what I'll do is I'll write A11 here. Okay. So what does, and I am writing it like this, because I just want to distinguish, because this is something known to me. These are the quantities that are known to me. So A11 here stands for the cost involved in transporting 1 unit of the product from source 1 to destination 1. Okay. Similarly, A12 would be the cost of transporting from source 1 to destination 2 and so on and so forth. I have A1n here. Okay. Similarly, I'll have terms like A21, I'll have A22, and I'll have A2n. Okay. Similarly, the last one here in between, of course, you have all the entries in between here and here also. And the first entry here would be AM1, this will be AM2, and this will be AMN. Okay. Now, but the problem is that source 1 has limited capacity. It has limited availability. Okay. Let's say that the total availability with source 1 is A1. So I'm writing the all the availabilities here. Right? Source 2 has limited availability, A2, and source M also has limited availability, AM. Okay. Similarly, if that means if I read this table row wise, I am getting the information related to the sources, right? But the demand, this is my destination 1. Okay. So the demand of this destination 1 is say D1, okay, or let's call it D1 or let's call it B1 because it will be easier for us. Similarly, the demand for destination D2 is B2 and demand for destination DN is BN. Okay, so they are my total demands. So I have availability, or we can write it as the total capacity also. Okay, we can call it as the total capacity also. And this will be my total demands, right? Now, one thing that is clear from here is that my variables here would be something like if I say x11, that becomes my decision variable when the number of units, that means this is what I have to find, the number of units that need to be transported from the first source to the first destination. Similarly, x12, x1n. So they are going to be my decision variables, x21, x22, x2n, and so on, xm1, xm2, and xmn. They are going to be my total allocations. We call them as allocations because we are going to allocate, I mean, finding decision variables in these kind of problems is as good as finding allocations, you know, how much to be allocated from which source to which destination so that all the total availabilities or the total capacities are also exhausted, and at the same time all the demands of all the destinations, they are also fulfilled. Okay, so this is how this problem is going to work. Okay, so if I say that if I have to translate it in the form of a linear programming problem, my objective function is definitely going to be the cost function, which is I define as Z, and I have to minimize it. Okay, so the total cost involved is going to be calculated from these cells only. Okay, so this is the first cell, this is the second cell, and so on, right? So basically, it's like a matrix, right? And this has an order of the form m cross n because I have m rows and n columns. And how many entries is it going to have? Definitely m into n. So mn number of variables I'm going to have, right? So if I say if A11 is per unit cost involved for this cell and how much am I transporting is X11. So the total cost for corresponding to the first cell is going to be A11 into X11, right? Similarly, for the second cell, it's going to be A12, X12, and so on. The first row, last entry is going to be A1N, X1N, right? So these will be the total entries corresponding to the first source. The cost involved from first source to all the possible destinations, right? Similarly, I'll have terms like A21, X21 plus A22, X22, and so on till A2n, X2n, right? Second source, and so on, so forth. The last entry is going to be something like AM1, XM1 plus AM2, XM2, and so on till AMN, XMN. Okay, so I'm going to have M into N number of variables, and this is going to be my objective function. Okay, is this clear? So far, so good. Yeah. Now, once my objective is clear to me, I have to minimize this. The next thing that I have to list down is what are going to be my constraints. Okay. Now, the constraints are definitely going to be defined by what is my availability, like this one, and what are my demands. Okay. Now, let's see how to define the uh, restrictions or the constraints depending upon the sources. Now see, the source S1 is your first source. Okay. Now first source cannot supply more than A1 units. Okay, because it has only this much available with it, right? So that means whatever allocations we make in the first row, they cannot exceed A1, right? So say supposing I have the first source has, say supposing 10 units available to me. Okay, and this 10 units have to be supplied to say 5 destinations. Okay, so definitely the number of units supplied to each destination cannot be more than 10 because it does not have more to supply. Now when we are making allocations, it could be that all these 10 units are supplied to only one destination, right? So that means source 1 will supply to that destination and will not supply to others. That's fine with us because we are making allocations. So it's like we are allocating that which product should go from where to where. Okay, so that means the first limitation that can be talked of will be in terms of total supplies. How much can we supply from each source? Definitely not more than what it has. Okay, so that means, and not just that, because not more than what it has would mean that we are talking of inequality here. That one option could be like x11 plus x12 plus x1n has to be less than or equal to a1. Okay, that is one option. But then at the same time, we don't want that the source should be left with some amount also, because unnecessarily we'll be putting on holding costs. Like see, the situation could be that these sources are my warehouses, right? I have put my products here. Now I want them to be supplied as early as possible because I'm paying the rent for that warehouse also. Okay, so obviously I want my warehouse to be empty as and when required. So definitely not just, I mean, the total supplies should should be such that the total availability is all exhausted from that source. Okay, so that is why when we talk of constraints in these kind of problems, they are exact equalities, they are not inequalities. Okay, so that means the first constraint that is going to be defined will be that total amount supplied from source 1 to destination 1 plus x12 and so on so forth plus x1n. Now this becomes the total supplies that can be allocated from source 1, right? And they should be equal to how much? A1. Is this clear? That becomes your first constraint. Is this clear, girls?
Yes, ma'am.
Right. Okay. Similarly, we can have similar set of constraints for all the sources, right? So that means I'll have x21 plus x22 plus x2n will be equal to a2. Now, how many such constraints? As many supply sources, how many? M. So, my last in this category would be xm1 plus xm2 plus xmn equal to am. Okay. These constraints are how many in number? Obviously m, and they are called as the capacity constraints because they are the constraints due to the limited capacities available with the sources. Okay. Now, as I said, we can read this column, we can read this table column wise also. And column wise, we were getting all the information related to our destinations. Okay. Now, look at this, the first column now. The first column is related to the first destination where we need to supply the goods, right? Now, the first destination needs B1 number of units. Okay. So that means whatever the demands of this destination is, see, if I read this X11 is the demand or is the allocation that can be met with first source to first destination, right? Similarly, X21 is the allocation that we can have from second source to the first destination and so on and so forth, right? That means X11 plus X21 plus XM1 is the total allocations that can be made to the first destination. Okay, but the first destination does not need more than B1 units. So that means if I add these allocations column wise, they should be exactly equal to B1 because I don't want the supply to be either more or less than B1 because the destination 1 needs only B1 units of that product, does not need more, does not need less. Okay, so that means the column wise constraints would be the constraints due to the requirement or the demand constraints. Okay, and how many such constraints I'm going to have? N number of constraints. Okay, so that means I have another set of constraints with me which I can write as the equations corresponding to those constraints would be something like x11 plus x21 plus xm1, which should be equal to b1. Similarly, x12 plus x22 plus xm2 should be equal to b2. And how many such? It will be x1n plus x2n plus so on so forth. Now I am adding all the variables but from the columns. Okay, xmn, they should be equal to bn. So how many such constraints? Obviously n in number. So that's why they are also called as the demand or the requirement constraints. Okay. But then, of course, because I am trying to write it as a linear programming problem, so obviously, and we are talking of physical allocations of products, so obviously they cannot be negative. At the most, क्या हो सकता है? कि we will not supply anything from a particular source to a particular destination. So that means the minimum that we can have is that any xij is 0, but definitely not negative. So that means all my xij's, they have to be non-negative. So for every I and for every j. Okay. So this becomes my problem now, right? So, and as you can see, it is a linear programming problem, right, with a minimization objective and exactly equality constraints. Now see,
Excuse me, ma'am.
I mean, it's not a problem. We are happy with it. We have been able to frame the problem at least. The only thing that I observe here is that this problem is going to have mn number of variables and m plus n number of constraints. right? So these many variables and these many constants, depending upon how many sources do I have and how many destinations do I have. Okay. Now, one option is, of course, you have framed a problem. It's a linear programming problem. We can solve it. We just need to, have a set of artificial variables with us. So obviously, m plus n number of artificial variables, and then we can proceed on because we have learned how to use simplex method. Okay. Now, what
Excuse me.
happened was that as the subject proceeded further, or as we moved on, it was observed that okay, it was observed that if you increase your number of sources and if you increase your number of destinations, and if we follow simplex method to solve the problem, there were two things that we observed. Number one, of course, it will become tedious. बहुत ज़्यादा हो जाएगा. So supposing you have, say, 20 sources and say 15 destinations. So imagine the number of variables and imagine the number of constraints, imagine the number of artificial variables that would be incorporated, and then we are solving the problem. So obviously that is one aspect, that it becomes tedious for us to solve. Okay. So what the researchers thought was, let us find an easy way out, to solve this problem, and then see under what conditions can we be sure that a solution for this problem will always exist. Okay. So for that, we'll go back to the problem itself and then see what could be the various options. Now, one thing that we observe from this table is that, okay, these are my total availabilities, right? So if I add A1, A2, AM, then that is going to be my total availability of the goods that I have, right? Similarly, B1, B2, Bn would be the total demand, right? So basically, what I am trying to say is that, let us, that what I'm going to say, what I'm trying to explain here is that we have also to see what are my total availabilities and what are my total demands before I start making the allocations. Okay. So what I'm trying to compare, the two values that I'm trying to compare are, I'm trying to compare what is sigma AI, where I varies from 1 to n. Okay, so basically I'm talking of the total availability here, and sigma Bj, where j varies from 1 to n. Okay. Now, if I want the demands of all the destinations to be fulfilled and all the sources to be exhausted of whatever was their availabilities, one thing that I need to be sure of is the fact that they should be equal. जितना है वो पूरा सप्लाई करना है, राइट? एंड जितना जरूरत है वो पूरा भी मीट करना है. तो वो तो तभी होगा ना when my total availabilities are equal to my total demands. Am I making sense?
Yes, ma'am.
In case this happens, then the transportation problem is said to be a balanced transportation problem. Okay, that means if sigma AI is equal to sigma Bj, that is, if the total supply is equal to the total demand, then the transportation problem is said to be a balanced transportation problem. And the researchers observed, and that is why, we developed a theoretical proof for the fact, it says that, shall I write it? Okay, I'll write it. The theorem says that a necessary and sufficient condition uh, for a transportation problem, I mean, whatever I have mentioned above, I mean, this problem that I wrote here, let's number this as 1. For the problem 1 to have a solution is sigma AI is equal to sigma Bj, where I varies from 1 to m and j varies from 1 to n. So it becomes a necessary and a sufficient condition. That means that the above linear programming problem, which is what? Which is actually a transportation problem, will have a solution if sigma AI is equal to sigma Bj, and if sigma AI is equal to sigma Bj, then this problem will always have a solution. Okay, so this theorem was actually proved. Right? So once we have this result, and if we have to solve a given transportation problem, the only thing that I need to check is whether my transportation problem is balanced or not. If it is balanced, it will definitely have a solution. How to find a solution, we'll come to it later on. But first of all, you see, before we begin on to frame or begin to devise, design certain techniques to solve one typical kind of a problem, we must first of all ensure that the problem actually has a solution. Okay, so that is why this theorem was important, right? So once we are sure that the problem is balanced, that the given transportation problem is balanced, definitely the problem will have a solution. Okay, so the next thing that we are going to look into it is how to find that solution. Okay, so that is why whenever we are given a problem, a transportation problem to solve, the very first thing that we are going to check is whether the given problem is a balanced transportation problem or not. If it is balanced, then only it will have a solution. Otherwise, it will not have a solution. Okay. Now, once that means the first step. Now let's see the various steps that we are going to use to solve a given transportation problem. The first step that we are going to use is to check whether the problem is balanced or not. Okay. Now let's discuss this step only first, and then we'll move on. Okay. If the problem is balanced or not. Now, if it is balanced, we move on. Okay. If it is not, then what we do? Okay. Now, it's not very tough to convert an unbalanced transportation problem into a balanced one. We just have to see which is greater. I mean, which is more, availability or the supplies or the demand. Okay. If the availability is more, okay, we can see mathematicians are very clever. More than half of the results are based on assumptions, or more than half of the results are based on the facts. Okay, let us create something dummy. Okay, physically it does not exist. That's what we did. We to convert inequalities into equalities, we created slack variables, but definitely they had their economic significance. Similarly, here also, what if the problem is unbalanced? We have to see an unbalanced problem will have only two options. Either my supply will be more than demand, or my demand will be more than the supply. That is the only possibility. If they are exactly equal, they are balanced, right? So supply and demand means total supply is more than the total demand, and total demand. So let me write total here. Total supply is more than the total demand, or total demand is more than the total supply. That is the only possibility which will make your transportation problem into an unbalanced transportation problem. If they are equal, it is balanced, right? Now, if my total supply is more than total demand, that means I have more to give. Okay. So what we can do is we can create a dummy destination. Okay. That means it's a destination which physically does not exist. But because I want to solve the problem, so I'm creating one destination. So that means whatever supplies we make to this dummy destination are not going to be actually supplied anywhere, right? But then I also have to see what are the various allocations that can be supplied to the actual destinations that actually exist, that physically exist. And since my result is in a way limitation on me that the problem cannot be solved unless and until it is a balanced problem, so somehow I have to make an unbalanced problem into a balanced problem. So definitely if my total supply is more than total demand, I know that some of the warehouse is going to be left with something extra which it is not able to supply anywhere. Okay. So that will be the amount allocated to the dummy destination, definitely. Okay. So we create a dummy destination and we convert, I mean, we create a dummy destination, and to this dummy destination, we allocate the demand as the difference of the total supply and total demand. Is that clear? Similarly, if I have total demand being more than total supply, that means I have the destinations require more than what I have. So definitely some of the destinations are going to be left unmet with. Some of the demands are going to be left unmet with. So in this case, what we'll do is we'll create a dummy source. Okay. And we'll allocate an availability to this dummy source, which will be equal to the difference of the demand, total demand and total supply. Okay. So the moment we have an extra column or an extra row, and then you add up, your unbalanced transportation would be converted into a balanced transportation problem. Is this clear?
Yes, ma'am.
Is this clear or not? How to convert an unbalanced transportation problem into a balanced transportation? Okay. If there is a doubt, please ask me right here so that I can move on. Is there any confusion on this? Huh? Let me see. Uh, okay. Swati, I just saw the chat box. Is your query clear now? Why we are taking equalities and not inequalities?
Yes, ma'am.
Okay, fine. So we move on, right? So now once we are ensured of the fact that my problem is balanced. So because of the result that we have with us, we know for sure that this problem will have an optimal solution. Okay. An optimal solution means we'll be able to find allocations which would account for the total minimum cost involved in it. Okay. Now come to the second step where we are actually solving this problem. Okay. Now, as I said, we can apply simplex method and then solve it. But as I said, it will be too tedious a process. So what the researchers did was that, okay, let's see what exactly is simplex method doing and how can that be tweaked a little, and we can devise another way of solving a transportation problem. See, what does simplex method do? What does simplex algorithm do? How does it work? It starts with an initial basic feasible solution, right? It computes the value of the objective function. It tests whether it is optimal or not. Okay, this is what we do. We we start with an initial simplex table, right? We get some value of z there, which is the value of the objective function at that stage. We check for the optimality in the sense that we look at all zj minus cj's. If they're all positive, we, we conclude that it is an optimal solution, we end. But if one of them is negative, then what we do? We move on to the next iteration. So that means what we are concluding here is that it is not an optimal solution. This is what we are doing, right? So basically, the process is start with an initial basic solution, check for optimality. If optimal, stop. If not, move, right? So the same logic was applied here, right? So what the researchers said was, as a step number 2, we are going to look for an initial basic solution. Okay. This is what we are going to do as a second step. As a third step, we are going to check for optimality. This is how we are going to proceed on, right? Now, to find the initial basic solution, instead of actually applying simplex algorithm, the researchers came up with various possible options. Okay, what they said was, we need an initial solution, right? So why talk of artificial variables? Why incorporate more variables here? We can devise methods and start with some basic solution. But definitely, because we have n plus n number of constraints, so we have also talked of degeneracy and non-degeneracy in simplex algorithms. All that was kept in mind, and it was suggested by various researchers, and we have various methods, to start with what we call as the initial basic solutions. I'll just give you a gist of it, and then we'll move one by one. To find the initial basic solution, the first method that we are going to talk of is what is called as the northwest corner rule. Let me write it properly. Okay, or just this thing. Northwest corner. So I'm writing it as NWC, northwest corner method. What it is, I'll just tell you. The name itself will tell you that. Second is what is called as least cost method. Okay. There is another third, which we call as, because it was given by Vogel, so we call it as Vogel's approximation method. Okay. So these are the 3 techniques using which we can find the initial basic solution. Okay. Now, what is an initial basic solution? Basically, see, your variables here are xij's, right? So, and how many of them? M into n, right? Now, how many constraints? M plus n. So basically, we'll be needing m plus n minus 1 number of basic variables, right? Xij's, out of those m into n, will identify which one can be basic, right? So once they become basic, all other become non-basic, right? So this is what simplex method does. We start with basic, all other are non-basic. Then what do? We check for optimality. If it is not optimal, then definitely one non-basic becomes basic and one basic becomes non-basic. Same thing will be done here. Once we check for optimality, then what will happen? That some non-basic will have to become basic. That means some cell where allocation has not been made, we'll have to make an allocation there. And some cell where we have already made an allocation will be removed from that list, because one basic cell will have to become a non-basic cell. Okay, so this is what we are going to check in the optimality condition. And for optimality, we have only one method, which we will be doing one method, though there are other also stepping stone method here, but we'll be doing only one method, which we call as the, this has got nothing to do with the name, please. We call it as the Modi method, but actually it stands for It's easier to remember like this. And I think when this method was developed, our prime minister was not even born probably. So we have what is called as, this is also called as the modified distribution method. Okay, so MO from modified, DI from distribution. Okay, so we call it as the modified distribution method. So what we do is we check for optimalities. If it is optimal, we stop. If it is not optimal, we modify the distributions. Okay, we modify the allocations that have been made, and then we move on. Okay? Then we get another set of basic solution. Then we check for optimality. So that means we proceed on till we reach an optimal solution. Okay, so this is how this algorithm is going to work. Okay, so basically, it is, as I said, we are not directly applying simplex method here. We are just using simplex method in the background, but then another set of algorithm has been made, another set of solving technique or solving procedure has been devised, which will solve our transportation problem. Okay, so this is the introduction to the transportation problem that I was planning to give you today, and I have done. Next time, in my next class, we'll start with each of these methods here. You know, we'll start with one problem and then we'll see. We'll start with initial basic, how to find the initial basic using all three methods. We'll do. It's up to you, but they are good in the order written. Okay, see, which initial basic solution would be termed as good? Obviously the one which is closest to the optimal. Okay, so northwest corner, it's the easiest probably, as the name suggests, but a little far from the optimal solution. Similarly, least cost, slightly more tedious than northwest, in the sense that you have to do some more calculations compared to northwest, but still it's better than northwest in the sense that it's closer to optimal solution. Vogel's, you have to do more calculations to find initial basic solution using this method, but it's the best because most of the times the basic solution obtained from Vogel's turn out to be optimal. So you don't have to work here, right? So if you use northwest corner, you'll have to work for optimals. But if you use Vogel's, maybe you don't have to work here. So either ways, we can use either of these methods and then we'll solve our given transportation problem. Okay. So in the next class, I'll start with the procedures, the techniques, and the algorithms of solving the transportation problems. And we'll begin with northwest corner and then move on till the optimal, to getting an optimal solution.